This is a 2 dB attenuator. I have found it noisy in a previous experiment that was with a vacuum tube oscillator, and the video is nerds28, and I can show some little detail from it. Here is another bad attenuator. It's 2 dB, and I have now the signal directly, and it's fairly stable, and I insert this attenuator. And the noise floor goes up by 4 dB or something, but the signal has gone down by 2 dB. So this one is very noisy also. I will compute how noisy it is later on. And the 2 dB BNC attenuator, 9.5 dB of excess noise in dBc per hertz, and this is at 50 kilohertz, and presumably this is AM noise. And that is the noise above the noise floor of this test, which was minus 194.7. So I will now check the noise of this attenuator at much closer spacing, because now I have the interferometry set up so I can do that. So based on my previous measurement in the nerds28 video, I should expect minus 185.2 dBc per hertz at 50 kilohertz separation. Here is the interferometric setup. And for all the details, look at the previous video. What I've done now is to insert this test object on the output of one of the oscillators, and I have set a matching 2.2 or something like that dB attenuation here, and fine-tuned on this variable attenuator to get a good balance, as you can see on the upper track. If I tune a little bit, you can see how the cancellation of the two signals is fairly good. The first step is to set a reference signal 70 decibels below the carrier. So first I make the carrier show 0, and then I adjust the generator to show minus 70 at an offset of 50 kilohertz. So I inject this signal, and I have set calibration, so now it shows minus 70, and I check the carrier. I have to click on it, I had to have it in the filter center, and then I can read it out here if I have patience enough. It shows 0.00 something. So the two signals differ by 70 dB. And I now look at the output of the interferometer. And you can see on the balance there are two signals here now. And if I try to make the balance better, the other one is that extra signal, this one that I added, which is 70 decibels below the carrier. So I place that signal inside the filter. So I have set the bandwidth to accurately 1 kilohertz. You should be able to see, perhaps. And the S meter to show minus 70. And then I switch off this oscillator. to see what is the noise. And what I see here is minus 155.2. And I checked the balancing. I will just make it a little bit less good, like that, to verify that it doesn't change the noise floor I see. There are some little spurs that come up, but if I make very good balance here, well, this is non-trivial because there are some thermal and other stability problems. But you see, this is reproducible. This is the noise floor I actually have from the interferometer. Minus 155.2. So with the bandwidth of 1 kilohertz, that becomes minus 185.2 dBc per hertz. It happens to be far closer than expected to my previous result. The interferometer itself, as I have measured before, is, you see, 190 is at his line, and the measured result was minus 191 for the interferometer. So what I find now is about 6 decibels worse than that. So I should subtract some small number because of the noise of the interferometer itself. But I'm not interested in that. What is interesting is what happens at closer frequency separations. Now I am at 10 kilohertz here, and the noise level is minus 150.07 or 08, minus 150.1, let's say. At 5 kilohertz, I see minus 147.4, and I will verify that the calibration hasn't changed, so I switch on that. I have set it to 5 kilohertz down, so it comes at the center of the filter, and it is pretty close to minus 70. It should be, because there is no selectivity involved here. So it shouldn't matter at what frequency I have this reference minus 70 dB signal. Now the frequency separation is 1 kilohertz only, and I have set the bandwidth to 100 hertz because the noise floor is no longer flat enough to allow a wider bandwidth. Means things go slower, and I have to read the noise floor here, minus 148.3, and I check the calibration because I have changed the bandwidth. But that shouldn't make any difference. 69.995, close enough to 70. And I check the balancing again. The amplitudes are drifting, and also the phase a little bit. And it seems it became a little bit lower. Minus 148.3. At 500 hertz offset I have these spurs, so I have set the bandwidth to 50 hertz only. And I have to be a little bit careful not knocking on anything, because there are stability problems. If I bend a cable or something, the balancing gets destroyed. But now it is very good, and I don't know why I see an instability here. It could be the attenuator, the test object. Anyway, I take this noise 144.8. Well, I had here 144.9. And again minus 145.1. So I wait a little bit. Minus 145.4. Well, I adopt this. At 50 Hz offset there are more spurs, and I have set the bandwidth to 10 Hz to avoid them. And the noise floor I observe then is minus 124.6. The spurs depend critically on the balancing, so I have to keep that good all the time, otherwise these things come up. Now the frequency separation is 20 Hz and the bandwidth 10 Hz. And I see minus 113.5 means 123.5 dBc per Hertz. This is a separation of 10 Hz at a bandwidth of 2 Hz. And the level then is minus 113.8. I have set the attenuator in front of the Percers and its low noise amplifier to 30 decibels. That's a lot of attenuation. And then I have switched 1 dB on this stepped attenuator to unbalance the interferometer by 1 dB. Means I get a very strong carrier here. I have also added here a signal from this audio generator, and that creates sidebands here. And if I change the frequency, of course they change. Now I have set Linrad to send the baseband to the network, and I have set it in mode coherent 2, which means Linrad will select this carrier within the narrow filter and use that for I and Q detection of the entire passband. And this is what it looks like. You can see that the red curve is much higher. This is the modulation frequency. If I tune it, you can see it changes. And I can now adjust the phase with the normal phase adjusting knob to get the green curve corresponding to AM modulation very low. Now I have zero attenuation and an unbalance that is not so big anymore, and I have adjusted for the phase modulation to be fairly strong compared to the AM. Means I'm tuning this for the minimum here, and that is also minimum on the green track. If I go 1 kilohertz away, there is more AM than phase, but if I go a little bit further away, the difference between phase modulation and AM modulation is much bigger. I see something like 10 dB, and that's expected and probably very close. The noise from the oscillators dominate, and they have phase noise, probably. I have removed that attenuator now, and I'm trying the interferometer for AM noise and phase noise with only the oscillators. And of course, attenuators and all the other stuff that could cause AM noise, perhaps. Now it's clear I have a correct phase relation. I see the added modulation in the red curve. I switch that off. And then we can see that phase noise dominates at close range. And I click a little bit away. And then I find that AM noise dominates, but not by much. Difference is very small. And at 2 kHz AM noise and phase noise are equal. So I can see the two kinds of noise this way. I have plotted the results on this graph that I made previously on the interferometer. At 50 kHz, the new point is significantly higher than the interferometer result. But when I go closer in frequency, something like about here, it says 3 means 1 kHz. The difference is no longer so big, and then the curves follow a little bit up and down. So this is the accuracy, which is not so good at the very close separations. Anyway, conclusion is out here we have AM noise dominating, as was clear from the direct measurement of the AM noise. 10 dB higher than the phase noise, roughly. And then, here, the AM noise disappears under the phase noise of the oscillators. So, attenuators give AM noise. Whether that is harmful or not depends on what you are doing, continuing with the signal. Sometimes AM noise is very dangerous, sometimes it is harmless.